All right. Uh, I will finally get started. I know why it was crashing, so I'm going to start with that. And it has to do with Docker running on Mac, and I suspect it'll also happen on Windows, which is that it runs through a virtual machine, which requires a certain amount of memory set to it. And by default, if I click on the whale and look up preferences, this is set to 2 gigabytes of RAM. And the particular thing that I was trying to run goes beyond 2 gigabytes and hence was crashing. Once I set it to 4 gigabytes, it didn't crash anymore. So I thought I would start with that because that's something that you could run into as you're running various Docker containers. And it was crashing in a weird way. The process would just get killed. It didn't tell me I'm out of memory or anything. So that would be something to keep around when you're using Docker. We're going to use the same container that we used in the morning, the NiPipe level 0 container, because it contains NiLearn that we can use. But before I get to that, I'm going to kind of go over some elements of machine learning. But I'm assuming all of you were able to download that container. If somebody doesn't have it, I would suggest for the moment to sit next to someone who has it. It's not the NiPipe tutorial one. It's the much lighter weight NiPipe level 0 container. Okay, but before I start, a few things. Well, I think this is kind of self-evident, but it's something to keep in mind is that a model is as good as one's prediction error. And what needs to be kept in mind over here is what is prediction error. And over the next couple of slides, we'll kind of go through that bit of it. Okay, there are pointers. These essays, I think they're still available, but I can put pointers to it. The other two elements of statistical learning is a free PDF download that you can get. It's from Stanford. It's a great book on machine learning. And Wikipedia obviously has lots of different components of machine learning. There are many different kinds of machine learning problems, broadly categorized in kind of this 2x2 matrix, which is you have supervised things where you have a target that you're trying to predict. And that target could be continuous or it could be categorical. And then you have unsupervised, and even in that space, you have continuous and categorical things. So you have dimensionality reduction, things like PCA, an approach to reduce or restructure data. Categorical, you might be trying to create clusters out of distances within data. Now, I'm not going to go into all of these things over this duration of the tutorial. The examples we have, which are from the NiLearn website, are going to be primarily about figuring out if voxels can predict categories. So we'll get there in a bit. Okay. It's a broad space. There are lots of things one can choose from when it comes to machine learning. And much like the world of deep learning has kind of become figuring out the right sets of architectures and parameters that suit your problem, machine learning in general is kind of trying to figure out the right set of models and features that suit your problem. And this is a nice decision-making process. Most of us would probably just stop right after start because we end up looking at brain imaging data sets which are fairly small in size. So the first thing you should think about is increase the size of your data set if you're doing brain imaging, because you're going to run into issues if you have a small data set. Yes? What do you mean by big? Larger than 10? No. I think it depends on the problem at hand. So the example that I'm going to show, I'm using one person's data, but it has enough samples to deal with some of these learning problems. So it's really about sample size. It's not so much about number of subjects, because the application might be you were trying to predict something within a subject. But if you're trying to do something across subjects, it really depends. I mean, just like statistics depends on effect size, machine learning also depends on effect size. If you have a weak effect, you're going to need more subjects. If you have a strong effect, you might be able to build it out of a much smaller set of samples. What it is, I think, is always dependent on the case at hand. I can't say a general number, although this thing, I think, says move on if it's greater than 50 as the thing. But that's, I think, really a rule of thumb in some ways that is dependent on the application at hand. Okay. So in terms of lexicon of machine learning, this is kind of puts a few words out there that's good to just have in your vocabulary as you talk about it, think about it. And we'll go through a few of these things. So underfitting, overfitting, you've come across these terms probably. And what we are really looking at is this difference of testing a model on out of sample data, so things that you didn't use to train the data. So the training error will keep decreasing as you increase model complexity. So what does that mean? As an example, let's say you have a linear model and you keep adding features to it. And it could be random features that you add to it. But as you keep adding, you're going to fit more and more of the data, and your training error is going to decrease. By adding more features, you've increased model complexity because it's a more complex model, you're fitting more parameters. But that doesn't mean that your test error is going to decrease. So when you take that model and test it on out of sample data, it doesn't mean that that's going to decrease. And that's really going back to kind of the title of this slide, that your model is as good as its prediction error. So when we say prediction error, it's how well that model predicts something that it hasn't seen before. And that's your real evaluation of how good the model is. And this difference between training and test error is sometimes referred to as the optimism of the model, because you can kind of say, if my model is telling me it's really good, it's being too optimistic when it really isn't. And so one of the things to keep in mind is that you're always looking at how to minimize this test error. That's what you're trying to accomplish with your models. So these are also terms that you might come across. What are bias and variance of a model? So this is schematically taking the idea of a target board. So if your target is the red dot in the center, that's what you're trying to achieve with your model. If you have a cluster of predicted scores that are clustered with low variance, but high bias because you're different from where you want it to be, right? The same thing is you could have low bias and low variance. That's where you want to be with everything. The real world isn't quite that clear all the time, but that's where you want to be. You want to be very accurate, and you want to have low variance around it. And you have correspondingly high variance and high bias. This is probably the worst place to be, high bias and high variance. But these are things that you're kind of trying to tune with respect to things. So where are sources of some of these things? I'm going to skip that one. So let's assume we're doing a study in depression. We send the sign-up URL to 50 email addresses from the BCS subjects list, which is a local list over here. We send announcements. We follow up with people who respond. We ask if they're depressed or not. Let's say of the 50 people, 30 people responded, and 16 of them said they're depressed. Would this data set be biased in some ways? Yes, no? What are some possible sources? Yes? So you could have bias inherent. I mean, we are using an email medium to send out a list of things. So let's look at a few things. We only sample from the mailing list. So that could be a source. So we include people with email addresses. Now, these days, I would say this is less of a bias because almost everybody tends to have an email address. But if you were doing this 15 years back, this would be a huge source of bias, because you would be responding to one of the reasons we've stopped doing studies on undergraduates over here, because they create a huge bias in terms of the profiling of people around here. So we did not follow up with non-respondents, and they might have had a different behavior than the respondents. We did not try to weight responses by likeness to volunteer information, so some intrinsic characteristic. So there are many things one cannot control for when we run these experiments. So your data sets, unless you sample a really large set of things, could have inherent properties that might bias you in some ways. Finally, I would say we have a very small sample size. Depression is a complex disorder. Okay, so in general, the data set used to build the model is provided prior to model construction, and the modeler cannot simply say, let's increase the sample size to reduce variance. In practice, an explicit trade-off exists between bias and variance where decreasing one increases the other. And minimizing the total error of the model requires a careful balancing of these two forms of error. So those are things to keep in mind as you're thinking about applying these things. So this is kind of just going with the figures. So how do we manage some of these things? Fight your instincts. Instincts say reduce bias and ignore variance. Accuracy, 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 right? Keep that in mind. Bagging and resampling their approaches, and we can touch on these a little bit, ways that you can reduce bias and variance through choosing models which take in some of these into account. Asymptotic properties of algorithms. So machine learning algorithms are theoretical things. They all have nice properties and things that apply if you had infinite data and other things. So instead of going by pure theoretical properties of things, think about your application at hand. That's important when you're thinking about these models. As with that chart out there, there are lots of models to choose from. SVMs are not the only models. Yes, they may have really nice theoretical properties for certain settings, but they don't cover the general world of real-life data. And we have to understand overfitting and underfitting. Okay, so we think of this, let's see, this prediction error as training error plus training optimism. So whatever you're getting, right, as training error, given a given particular model, and this difference together with it gives you the prediction error. And we are trying to minimize that thing, the whole thing. So just reducing training error, insufficient to give us a good model. We want to come up with this best match of training error plus optimism. So I already kind of talked about how you can continue to reduce training error by increasing the parameters of your model. It will give you better and better fits. So that's not where you want to go. So how do you measure error? And people have come up with various things over as they've thought about this. The thought process behind reducing prediction error isn't new. So we're going to go through a couple of things quite quickly. Adjusted R-square. So many people probably have used R-square in this room, right? Explained variance. Adjusted R-square penalizes by the number of features in the model. So you get lower explained variance if you keep increasing the number of things. Now, note that it's very easy to apply, but it may still overfit data because in general, you're applying this over the data that you fit the model to. You're just penalizing for having a lot of terms in it. There are some information theoretic approaches. I won't go into details. Again, some of these are easy to apply. There's lots of theoretical debate around this and requires models that can generate likelihoods. So we could say holdout set. Let's keep some data aside. And that's actually good because now you can break things up into a training set on which you build the model and you test on something that's kept outside. Well, that depends on the size of your data. If you're back down to 20, 30 data set, if you take out 10 points of the data, you might actually be reducing the distribution you study to a very small set. Also, how do you know what data you're throwing out is different from what you have in the training set? So understanding how the distributions of the training set and test set kind of are similar is important in keeping this. So you want the test set to have similar data as your training set. Okay. So in many cases that are practical, at least in brain imaging terms, we use cross-validation, where you can take out a set of data and use the rest for training and evaluate that trained model on the left out data. And you can repeat this process over different sets of data left out. And people can do this in various ways. So you can do what's shown over here, which is called k-fold cross-validation. This is a 5-fold cross-validation. You've left aside 5 folds of data as test sets, and you've trained on the rest and applied it to that. You can also do bootstrap cross-validation, where you randomly pick up data that you leave aside, build the model on the rest of the data, and test on it. And that way you build up a distribution of prediction errors as opposed to one single prediction error. So there are different ways one can approach this. We'll be looking at scikit-learn. Well, we'll be looking at NiLearn, but NiLearn is really built on scikit-learn as a platform for doing machine learning. And it has many, many different ways in which you can leave out data. And some of the things to consider are leave one subject out or leave one label out, for example. So you might augment data sets. In machine learning, we often do this, create fake data I shouldn't say fake data, create similar data with slightly different noise distributions that are similar to the data you have. And you might take one person's data, simple example, add different kinds of noise. It may not help your problem, but there are different ways in which machine learner folks have tried to augment data to increase the sample size. But then what you don't want to do is to do cross-validation on that augmented data set. What you really want to leave out are unique samples from your original data set in your test set. You'd never want to mix samples from there. So that's something, and if that's not clear, stop me right now, and I can clarify it further. But if it's clear, I'll move on. Yes? Sure. Okay, so let's say we have a data set from 1, 2, 3, 4, 5, 6 people up front over here, right? So one way of doing cross-validation is we have 6 points, and let's say we leave out 10%, well, okay, two of those points at a time. So we leave them out, we build a model with the data from the 4 of us, and test it on that outside model. We might find that having just 6 points is insufficient to train this model. So we might take each of our data and augment it, so we can create variants of the data. So let's assume that each of us now generates 10 data points. Not 10 new data points that we collected, but just from the data we have, we create a new set of 10 data points. So overall, we now have 60 data points. So I could run one of those cross-validations with k-fold, but that doesn't guarantee that the test set left out has unique people left out. And that's what you want to do with leave one label out or something. So now you can think of data points as having labels that come from each individual. And so now you want to ensure that what's left out doesn't have a label in the training set. So that's what I mean by augmentation and resampling. But these are ways in which you can boost the size of data sets to, in certain ways, to help you with your problems. Okay, so how do we choose models? There's lots of models out there. I have my favorite model, but I won't tell you that. There are some go-to models I go to for many things, but let's think about more strategic ways of how we choose models. Features and model parameters. Okay. So let's start with feature selection. Given any data set, you may have many, many features to choose from. And there's a lot of ways in which you can choose these features. And this is only a subsample of things that were in scikit-learn when I took this screenshot, which was over a year back. There are probably more at this point in time. But the general idea behind many of these things are to figure out ways to constrain your search space of features before you fit it into a model. Some simple things are just univariate selection. You kind of run a regression between your target variable that you're predicting and your features, and you find the features that are well predictive of that target variable. Note that this is all within your training set, right? And you use that as your subset of features. And there are more complicated things which actually use machine learning algorithms to get you at feature weights. Another way to do it is through this idea of nested cross-validation. So we've talked about cross-validation. Leave aside some amount of data for testing. What you can do is now, within that training set, apply cross-validation again. How that might help? So let's say I was running univariate feature selection. I might do something where on each fold that's left out within the training set, I get a set of features. And I might say, I might take the intersection of all the features across those folds as a way of reducing my feature space. Or I might say I might take the union of features. But if any decision I make, I'd like to do it within that nested construct. And that's true of models. So I might have a linear model. I might have a random forest model. And if I want to not demonstrate what the performance of each model is on an application, I might take the models and throw them into this nested cross-validation. So just like I'm selecting features, I could be selecting models. So which models perform best within a set of these folds? And then choose that, bring it up to the outer level, and train with that. People have created all kinds of other ways of doing this. So there are things like grid search, which are built into scikit-learn. There are extensions like hyper-optimization, which takes a set or ensemble of models and parameters and tries to find the best model and parameter setting. And then there's a class of things called super learners. Throw everything at the kitchen sink. As long as you have enough data, you'll figure out a way to optimize across those. Okay. But maybe this is a way of thinking about the problem space in imaging, that you really don't want to toss out exploration. So we think of things as playing with data, observing data. So we want to look at data. I mean, we want to see what things are related to it. We just don't want to get biased by it. And that's what science is about, exploring different kinds of data in various ways. A second phase might be doing this cross-validation. So now we have data, we break it up into training sets and test sets. We might do feature selection and model selection via nested cross-validation or an inner cross-validation, and then apply the model on the test set, average results, evaluate the outcome of the cross-validation. If we are happy with that outcome, because that tells us how good our model is, then we take all the data with those features and parameters and create a model. So now we have a model, but we can no longer use it on the data we have because we've used all of our data up. Now we might get new data, apply the model to that new data, see what the effect is, and then update the model with that new data. So whenever you get new data, you shouldn't really stop unless you have lots of data and you're not getting model performance improvements as new data comes in. But typically, as you start off with, as you get new data, you continue to update the model with the data till you reach some asymptotic performance. And then you say, okay, this model is good enough for things. And so you continue to apply it. So this is where, within limited sample things, it gives us a sense of how good our model is. But in terms of once you've done that, the model you want to publish is one that you train on all the data. You don't know what its performance is going to be outside. You only have an estimate of that performance through this measure saying, based on my internal evaluation, I think this is what the performance is. Okay, so I think we're done with that. So that's kind of the yes? Okay. So a couple of things there. So my feature selection itself could still be a cross-validation when I use the whole model, right? So I might still be looking at ways of reducing that space by looking at overlap of features or intersection of features. So you can do a couple of things in that space, which is you could look at a histogram. How often are certain features selected? And you could say these are more important features than other features that are not selected that often across the sets. Or you could aggregate everything and say, I don't care about how often they're selected. These are the most performant features, and these are what I would consider the most important features. Yeah. I will do, so here I'm doing feature selection within the training set of the cross-validation. Here I'll do feature selection on the whole data, on pieces of the data. I might do feature, it really depends on the model that I'm using. So there's certain models which inherently do feature selection. So if I'm using something like Lasso, which effectively has a way of reducing the feature space to optimize things, right? It creates a sparse model on its own. So it's effectively doing feature selection. But I could think about running Lasso on pieces of my data set because my data set may be small, and so those features may be noisier. So it really depends on how noisy those features are. If my evaluation over here suggested that consistent features are being selected, I'll use that. If my evaluation here suggests that every fold has kind of different sets of features, then I have to rethink how I do the feature selection. It can be, but so this is now getting into more advanced ways of doing feature selection. So you could look at features if they're correlated and create clusters of them. So there's an approach like dictionary learning. So you basically say there are clusters of features which are related to each other, and I'll put that in a bucket. And anytime I select features, I'm going to select one or two features out of that bucket. Right? So now we get into different ways in which you can do feature selection, but you can address some of these issues through different ways. So how do you deal with correlated features is an interesting and open problem in general, but there are ways people have approached doing some of these things. Okay, yes? Ah, so I would do this within this section again. So so instead of choosing features, let's say, I'm choosing models. So I do a nested cross-validation. I train, and models will have different levels of parameters. So if it's really overfitting, it won't do well on the left-out test set within that fold. So now I look at which model really did well, and this is where the word prediction error really comes in. It's the output of the model on left-out data, things that it hasn't seen. And on the basis of that, I will choose the model that performs best, and then use all of the training data and that model and its parameters and features to create it, right? So that's one way of reducing, choosing the most optimal model, so to say. Okay, any other questions? All right, are we ready to try some things? Okay, so as I said, that first one, and we're going to use the exact same command that we did before. Yeah, I'm going to even delete this. Oh, okay, so if you, Docker preferences, I would set the memory to 4 gigabytes. Now, maybe a little less is okay. 4 gigabytes work for me, so I'm just saying 4 gigabytes. You don't have memory? It's in advanced. Okay. Whenever Docker prompts me to upgrade, I upgrade. I'm a blind believer in living on the blood-sucking edge of things. That I don't know. The CPU is fine. It might take a little longer, but yeah, the crash that happened was a memory error. So I'm just trying to prevent ourselves from the morning fiasco of not having the latest version of NiFi in it. All right. Then I want you to go to nylearn.github.io. And again, this is, so for many people who do MATLAB stuff and other things, there are toolboxes out there. So Pronto is a very nice toolbox that exists that works with SPM and MATLAB and implements a lot of different functionality. My goal here is hopefully people can follow along if you're not familiar with Python, but it kind of gives you the sense of both the power of these utilities in trying to do machine learning easily with imaging data, but also about the things that we just discussed and how to implement them within the context of a tool. This will follow Python. I'll go slow. I'll talk about pieces. And if anybody has an issue that you don't understand a segment, just raise your hand and I'll explain it. Okay, so if you're on, okay, let me go step by step again. So I'm assuming everybody had Docker pull. You have restarted your Dockers with augmented memory. Yeah, all good. Whale back on track. Okay, and then you can run this command again. And when you run that command, it would have given you a URL in the window, and you copy and paste that URL into a browser. And you would have seen this without all those files. It will be empty just like you had in the morning today. Maybe you're already running a Docker on that port elsewhere, or running Jupyter locally in a different terminal. So just change the address to something else. And to change the address, the primary thing is this first set of 8888. I mean, I could call this 1234. And then a funny thing will happen because this URL will still say 8888 because that URL is generated inside the container where it thinks it's running on 8888, but you would have to replace it with 1234. So let me break that down. You have a container and you're running Jupyter inside that container. That container is like a machine, and you're setting, when Jupyter runs, by default, it'll run it on port 8888. But that's inside the container. What this Docker statement is doing is saying, I want to access that port in the container through this port 1234 on my local host or the container's host. And you're really doing a mapping from your local computer into the container's port. So now when Jupyter is executed inside, it couldn't care about your outside environment. It doesn't know that you have mapped 1234. It still runs itself on port 8888. And therefore, that URL wouldn't work anymore. And you would have to give it, so when Jupyter generates this, it's thinking inside the container, and it's thinking localhost inside the container. When I asked you to paste it, the semantics of localhost had actually changed. You're actually looking at localhost of your computer or the host OS in which it's running. Okay, so hopefully everybody's got it up and running. What we're going to do is go to nylearn, hit examples, And we're going to pick the decoding tutorial example. Here. So it's on the first row. It's the last example. It's called decoding tutorial. And if you click on it and ignore everything, because I really don't want you to be copying and pasting, at the bottom it says download Jupyter Notebook. Yeah, an introduction tutorial to fMRI decoding. Okay. Having downloaded it, I hope that you now know how to upload that notebook into the container. Okay. So you're on Nylearn's GitHub IO. There's a download button here. I'll download Jupyter Notebook. That'll download a file into your computer. Then you go to the Jupyter page, and here there's a tab called Upload. You hit Upload, select the file that you just downloaded, and it should appear there. Okay. So I'll point out Python things, Jupyter things, and machine learning things kind of simultaneously. This first line over here basically says, whatever figures you generate embedded in the notebook, don't try to create a window. We're running Docker. It's not connected to an X server anywhere. Those windows are not going to go anywhere. You're not going to be able to see anything. So what Jupyter can do is take the output of these plotted windows and paste it directly into the notebook. So that's what that first line says. If I hit Shift Enter, let me restart my kernel so that I'm in line with you guys. And it should have given you a 1, which means it has entered. So Shift Enter executes a cell. You could also go to the play button over here and hit that. That would also execute the shell. I'll skip I keep executing test cells. It doesn't have an impact. And I'll get down to this file. So what this is doing over here is that Nylearn has a bunch of different data sets directly available for download, formatted for doing tutorials and machine learning. So here we're fetching the Haxby dataset, which is one of the first datasets that was used to show multivoxel pattern analysis type approaches on brain imaging data. And in particular, it's getting dataset from one subject, happens to be the second subject from the dataset. No, so Nylearn is a wrapper. Well, I shouldn't say a wrapper. It's built on top of scikit-learn, so it has all the machine learning machinery of scikit-learn, but then it has elements that are useful for neuroimaging data sets. So that happened very quickly because I had already done this before and it had downloaded it. It'll take a few seconds for you to download that data set. It's not a very large data set, so I shouldn't say a few seconds. It's never a few seconds. But within about a minute, yeah, have it. Okay. So since this is a notebook, I can actually see what this data set looks like. Haxby data set. It's a JSON file which has all kinds of information. It has something about an anatomical image. It has a description of the study. It has a pointer to a functional image. It has a pointer to a mask. It has a pointer to other masks about other things. Okay, so one of the first things this tutorial does is takes one of those masks, which is the ventral temporal regions, which for somebody who does face processing or something knows that that's an area of the visual stream that will get activated. So they're subselecting a set of voxels of the image. And if we execute this, so this is where that matplotlib inline kind of comes in. It generates this image within the browser instead of outside. So it's simply plotting what voxels in the data set are in this mask. It's a little clearer, hopefully, on your computers than it is over here. At least you might be able to see an anatomical image behind those blue voxels. Okay. So what we now want to do is to extract the functional time series from those voxels, which is what the second piece does, Nifty Masker. So now what it's saying is, so a functional time series is a 4D time series. So you have these 3D images over time, and it's taking those mask voxels and extracting time series for each one of them. Okay. I can print this, just looks like a NumPy array. But I can also look at its shape. And this shape should correspond to the number of time points and the number of voxels in the mask. So now I've reduced a 3D data set into a 2D representation of samples by voxels. And most machine learning tools out there love 2D representations because you can treat each row as samples, you can break them up, you can parcellate them, and you can treat all the columns as features and deal with them. So, well, this data set also has some labels that we can get. Then in this particular case, it's going to keep data corresponding to whether that label, because people were shown different images during this functional task, belonging to faces or cats. Cats are a very important component of BrainHack, I forgot to say. Okay, so now we can look at it again, and because we've reduced the total number of samples to just faces and cats, we've reduced this now to 216 samples as opposed to earlier on, where we had 1,452 samples. We still have 577 voxels because that was the mask we used to take out the information. So now we also reduce, so our targets originally were all the labels, right? All the different types of images we were trying to classify. Now we've reduced that down also to just these relevant targets corresponding to the labels. Now we get into a simple classifier. And in this particular case, it's using a straight up support vector classifier to do things. So we import a support vector classifier, we specify the kernel to be linear, and that's kind of important for a step down the road. If we want to interpret the weights of this classifier, only the linear kernel support vector classifier allows us to relate the weights on the features to importance of the features. Any other form of kernel, you can't really take that information and say what's important and what's not. Mathematically, only the linear classifier gives us that And now training this is as simple as that command that I just executed and took all of a few milliseconds to execute. This is a relatively small data set at this point in time, and it does it pretty quickly. And now we can do prediction. So we predicted faces and cats. In fact, we can measure the error. And I'm perfect. So what's wrong? I used all the data. I basically trained and tested on the same data. And if there's one thing you take from this, never do that. Hmm? So, yes. So training error is 0 effectively, which is what, so this is prediction accuracy, right? So this is the flip of training error. We're looking at a value for accuracy, and accuracy is perfect because training error is 0. It didn't have to be 1. There could be noise and other things but it'll be really, really high because you are fitting a pretty powerful classifier to data and testing on it. Yeah. Faces and houses would be slightly different, but this is a pretty good classifier. Okay. So now we can look at the kind of thing that we talked about as one of the examples, a held out set. Yes? In this particular case, yes. Each sample is a session within that collection. What I can't remember is whether it's a summary of a block. I know that when they created the data, they chopped off edges of the, so because of hemodynamic response, they chopped off a few TRs relative to the onset of the block to ensure some level of independence across these labels. But I would have to look up exactly how they did that to let you know. Right, right. But within that, they could have left out edges to prevent overlap of signal between blocks, which is what I can't remember. Yeah. Correct. Or TRs. So they're calling it samples. So not these, all of these samples are not necessarily independent, right? Unless, so if they were indeed 2 TRs right next to each other, I wouldn't consider them independent samples in functional MRI. Now, if there were 2 blocks further apart and they were individual TRs, then I would say these 2, even if they were cats, are independent. Not that. Okay. So perfect prediction. So now we can do something like what we talked about, leaving out some subset of data. So this is basically saying, I'm going to leave out the last 30 samples of the 216 samples. I'm going to train on the rest. And I'm going to predict all the samples that were left out in that last segment. And we are no longer at that perfect prediction. So now we can go back to the next step, which is the cross-validation thing, which is now leaving out segments of these samples. I'm still not satisfied that these are all independent folds, ideally, but they're already a better thing than what was being done in the first place. So now it's breaking it up into 5 folds. So the 216 gets split into 5 segments. And it takes each segment and holds it out as a test set and uses the rest of the data to train things. Within the context of scikit-learn, or this is true of scikit-learn because it borrows from scikit-learn, this statement basically does that splitting. So this CV is an object of k-fold. So it takes the information about the total number of labels and creates a generator. And that generator says, I have a train piece and a test piece. And this will generate 5 different things because it's a 5-fold, it's a k-fold with n folds equal to 5. It'll create 5 separate test sets and train sets, or pairs of them. All good? Okay. And what we are looking over here is the prediction within each of these training and test sets. And you can see there's variability, right? So on some sets, it's over 70%. On some sets, it's below 50%. Now, scikit-learn does have something which can shuffle when you ask this generator to run. So each time it will be a random set, or it'll do a randomization of the samples before it does the splits. And so often what I like to do is run the bootstrap shuffle split. So I will say take out 10% of the data every time as your test set. And that's a personal preference. And I build up a distribution of prediction errors. So that kind of gives me a notion of how bad or how good I can be in the extremes of that distribution. And I think of it as a better way. So if that distribution is really narrow, I have a good, so it gives me an estimate of the variance of the classifier by doing that. So the splitting is not random. The splitting is exactly as she was saying, which is you take, so for a 5-fold, you take the first 20%, leave it out as the first test set, and use the remaining 80% as the training set. For the second fold, you take 21 through 40 as the test set, and use the other pieces as the training set. So the random part is on the data indexes that are done. So I'm going to pull that up very quickly, and I'll take your questions in a second. This will also show you a little bit of Jupyter. So I've just pulled up the help for k-fold by typing k-fold semicolon question mark in a cell and executing it. Right? And the help is here. And there are 2 things that control randomness here. Okay? One is this flag shuffle. So by default, it's saying, since I have not set shuffle to true, whatever order I give it, it's going to do this 20, 40, 60, 80, 100 split in that order. The other factor is random state, which is related to shuffle. So every random number generator on digital machines has a seed from which it starts. And depending on the platform, program, et cetera, that seed could be the exact same seed every time. So you get the same order of random number generation. Or you could force it. So if you're doing a test where you want to force a particular random order, you can set that random state to a particular state, and it will always generate the same sequence of random numbers. In this case, neither of them are coming into play because shuffle is false. So whatever the order comes in, it's going to take that, break it up into 5 boxes, and use that. So if the distributions of those boxes were weird because of where these cats and faces were, you could run into issues. Correct. So each time you hit shuffle, you would get different numbers because they're different sets. Oh. Correct. Because it's training and testing on different data sets effectively. I would think the average error would be roughly similar unless the non-shuffle thing was biased in certain ways. Yeah. Okay. So in this particular case, because the original order was based on time. Yeah. Yeah, so let me repeat that. So in this particular case, because this is an fMRI time series, and the way the data are arranged is with respect to that functional time series, where independence comes into play, uh, you have these blocks that are kind of semi-independent of each other by doing this. By shuffling it, you're mixing up these blocks. So you're taking time points that were independent and putting them together as or time points that, yeah, so you're taking time points that are dependent and putting them on both sides as in into the training set and the test set. Right. Yes. I will do that. Really good. So while one might use Shuffle for various things, the data set and the application you're working on has to be kept in mind when you're thinking about this. All right. So by default, so now we want to establish what the cross-validation score is. So we just printed out those errors. We could have taken the mean of those errors as the performance of this model. We can also use this thing called cross-val score, which automatically gives you the mean score across those fits, in this case, for every fold. But it uses a three-fold cross-validation by default. So cross-val score, I've not specified what kind of cross-validation it should run. Basically, we are taking this 5 lines over here and replacing it with 1 line over here. But by default, it uses 3 folds instead of 5 folds. So to change it, I basically augment this with the CV. So I take 5 lines and replace it with 2 lines because I still have to create that CV in 1 line. I could stick it directly in there if I really wanted to be compact and efficient. Okay. So this is just saying Nylearn, which is based on scikit-learn, has a set of functionality that helps you simplify how you do this cross-validation into almost one-liners. Okay. But there were a couple of questions, and I said I would take them. Okay. Okay, that's answered too. Awesome. I'm happy when things happen like that. So that's a good question. So how do you determine independence? So she asked, does it make sense to do k-fold if you have time series? And when it comes to time series, you actually have to be, it depends on what that time series is. In the case of functional MRI, where we have this very slow hemodynamic response, you have to be careful. But if you have a time series where the time points are relatively independent, k-fold might be just fine. Now, if there's dependence in that time series where you're really looking at different structures of data over time, so a chaotic time series, k-fold would not help in any way there. In fact, that would be a very poor predictor in most cases. So it really depends on what elements of the underlying generator you're capturing in terms of distribution. So what k-fold is basically saying is we want to create similar distributions of data between the training set and the test set. So if that is violated, then that's not a good way to do the division. So maybe you're getting into the realm where you're, again, taking pieces of it that are really dependent and putting on both sides, right? So in general, we assume that if you're doing a task, for most fMRI tasks, if you're seeing an image again later on, that's somewhat independent. That's not completely true either, but somewhat independent. Whereas the samples that you're collecting from seeing an image right next to each other are more dependent than one further down. That's not completely true, but it's a close enough approximation in this case. Okay, so we've got CV score. We do this, automatically gives us 5 numbers. But this is where kind of the rest of it kind of comes in with respect to this experiment, is that the best way to do cross-validation is to respect the structure of the experiment, for instance, by leaving out full sessions of acquisition. So let's take a look at session label. So they had 12 sessions where they collected cats and faces responses. And what they're saying is, I'm going to train on everything else. I'm going to leave an entire session out because there could be dependence within the session. It's doing pretty well, having left out a session. Or 12 runs. I don't know whether it was a session or a run, but yeah. That would be generalizing across subjects. So this thing is doing within subject prediction of saying, if I knew something about the subject, how well can I predict the state within that subject on a left out data set? But that's as interesting a question, which is, if I gave you 10 subjects of data and the Hagsby data set has this, how well can you create a predictor that can take an unseen subject and do things? A lot more interesting questions come into the picture there as to how you might relate individuals' brains to each other. That part is left out over here because it's all within subject. Okay, so given that this was a support vector machine, and again, this is not saying that this is the best model to use for this. This was just chosen as an example. There are many, many different kinds of models that could, and we're not even tuning any parameters of the support vector classifier, which itself has parameters that one could tune. So if you look at the coefficients, these are the weights associated with each of the voxels in the mask. And since you have weights associated with each voxel in the mask as a dimension of 577, you can apply the inverse transform, the same thing that we use to extract the voxels from the time series. So we had applied a masker up on top to extract these voxels. You apply the inverse transform, and now it takes these masked voxel, the coefficients, and creates an image. So you've gone back from a single vector, which was the mask, to a 3D image with one line. Why is that useful? Now, you can save it to a file, and you can plot it. So now you see the weights that show up. Again, I'm hoping it'll be better. I don't want to dim the lights at this point on your computer. So we've just gone through an example which kind of captures many components that we've talked about. How to do cross-validation, how to think about the experiment and think about what you're doing. It's also an example of how easy it is to use something like NiLearn and scikit-learn to do prediction. It's a few lines of code, really, to get all kinds of fun things going. This other example, I'm not going to go through it. You guys can go through it sort of independently. The main difference that this does is, instead of using this masker from the ventral stream that it used to pre-select a set of voxels, it actually uses an ANOVA to select the most relevant voxels within the context of the data. So it takes the whole brain, which is why it takes, this was the example which was crashing, which I asked you to increase the memory for, because now it takes the entire data set instead of just a subset. It's no longer 577 voxels. But it's the same exact idea. Now it introduces a couple of other things. So there's a pipeline within the context of scikit-learn. And this pipeline would be applied to training and test sets independently. So when this classifier is run, it will do the feature selection within your training set, do the model fitting with the SVC, and then it'll apply that same thing to the test set separately, where it'll use that same set of features from the test set. So that's one thing. The other thing that I did want to point out is something in this nifty masker, which actually can be avoided because you're using a pipeline. So what this is doing is, it says for decoding, standardizing is very important. But this is standardizing across the entire data set. One could standardize within the training set and apply that standardization to the test set. That would be a better way. That way because now if you wanted to apply this model, you would need the original data with you all the time to standardize against it. Whereas if you standardize only within the training set and apply those settings to the test set, then you only need the model which has the standardization parameters and apply it. So that really creates independence between your training set and your test set. So this is not quite the best way to do it.
Okay, so false.
So false wouldn't standardize as part of doing this, right. But what you can then do is come here and from learn.preprocessing import standard scalar. Standardize standard scalar. So now I have a pipeline that does standardization, feature selection, and model fitting within the training set and applies that to the left out data in the test set. Oh, here, yeah, that's overfitting. But cross-validation comes later.
So
no, so it's already. So think of this as a little work. Think of this as your model now. Your model does standardization, feature selection, and fitting. No. So what it does is, so what this will do is, this thing will store mean and variance of the training set. This will store indices of features chosen by running this feature selection. And this will store the model parameters, the support vector parameters. When it's applied to the test set, it'll use this mean and standard deviation to standardize the test set. Then it will select the same indices that were picked up over here during training, and then apply the model parameters. It's the right magic.
Yeah.
Yeah. So this really allows you to create this nice separation between training and testing quite nicely. Yes? So the standardize or standard scalar has to do with the distribution of values in a time series. No, it's not brain rotation. This is z-scoring. right? So it's basically saying I'm going to z-score the signal, but ideally you want to z-score within the training set and apply that scoring to the test set. Yes. Uh, so if you look at right here, ah, uh, so this goes back to how do you select parameters of selectors and things. Uh, I, I don't think this particular one, let me just take a quick look. I don't think this has a grid search in it. But what you could do is to say, I don't want to set the k equal to 500, which is done over here. I want to sweep through a range of values and choose the best number, and that's where the nested cross-validation part would come in. No, it could influence the output.
Yeah, but I mean,
So I don't want to speak for every application out there, but any parameter and any model could influence a given application. And a key question is, how do you figure out? And all we're saying is you don't figure out, you put it within this nested cross-validation so that you don't have to choose a priori some of these things. Okay. Are there any questions? Otherwise, I'll stop over here. Now, the Nyland side has a lot of examples of playing with this. The goal over here was to kind of give this idea of a cross-validation framework. It's, if you're doing any kind of prediction, you should look for it. So if you're running things in SPSS or R or MATLAB, you should ensure that you have this independence of training and testing within those things. So certain things from certain points don't implement nested cross-validation, for example. So one of the things that often happens is instead of doing nested cross-validation, which I haven't shown an example of over here, but there are examples on both scikit-learn and NiLearn's side of doing that. What people will do is they'll run a cross-validation, they'll look at the result, they'll go back in there and either tweak the parameters of the model or tweak the number of features being selected. You're biasing yourself by doing that. The whole point over here is that any decision-making process should be built into the steps as opposed to looking at your final score and deciding based on that. So each time one does that, whether it's model selection, whether it's feature selection, whether it's parameter selection for models, those shouldn't happen by looking at the result of the cross-validation output. Those should happen internally as some sort of an algorithmic way of choosing it. And that could take the form of grid search, it could take the form of hyperopt, and other ways of selecting those things. As a package, I've used both. Each has their benefits. I think PyMVP has a few algorithms. This is kind of clean, and because it follows the scikit-learn syntax, it's quite simple and straightforward to use. And there are many people using scikit-learn because that's a more broader general purpose package. So from even a package usage perspective, because there's a broader user base there, I think bugs get fixed better. So from a software open source standpoint, I prefer packages where bugs get fixed quicker or bugs are identified quicker over a specialized package where it's that process has a longer time cycle. I really like this idea of pipelining and being able to do things quite easily, almost with one-liners. Yeah, Yarek, Michael, and others maintain PyMVPA. Yeah, so PyMVPA is very focused on imaging, whereas scikit-learn was more general, and then NiLearn came about on top of scikit-learn as a more neuroimaging focused things. And they share a lot. If you use PyMVPA, you can actually call scikit-learn things from within PyMVPA. Some people are used to the PyMVPA syntaxes, and they would still be able to leverage all of this. Yep. So that depends on. It's very easy to implement Searchlight, and I think they have an example. A perfect place where radius should be in a inner search. Yes. So in a 2D data set, that structure goes away, right? There's no consideration. So you'd have to write your own feature selection thing, and people have done that. We've done that in the past, where we take in that inner loop, we get the features, turn it back into a 3D thing, do some kind of processing that takes a priori knowledge of that structure into account, and then extracts features out of it. So we could do clusters, for example, off of that, knowing that structure in place, and then say, okay, I don't want to over-select a given structure cluster. Right? So yeah, that has to be implemented, I think, on a case-by-case basis. There may be. Nylon has been improving quite rapidly. So it's possible that the last time I actually looked at the development side, that has happened. So I would highly recommend just browsing through the examples. And if you can't find it, just post an issue. And either somebody has extra code that does it, or if it's a reasonable feature, they'll include it within the context. Are there any more questions? Yes. I really like extra trees. It's a variant of random forests. It can get complex. It's slower than some of these other things to tune. On average, across a whole set of applications, its performance is near the top everywhere. So that becomes my usual go-to model when I run into a new application. It may not be the best. So again, when I do model selection, something else might come out to eke out a few percentage points. But in many cases, I'm not trying to eke out a few percentage points. I want a robust framework, and I really like extra trees. Also, a couple of things extra trees has is, like the linear kernel, it provides a set of feature importance vectors. So it tells you which of the features in your original data set are more important. So now, note that this is a multivariate space, so you can't just simply threshold things, but it gives a nice idea of some of these things. Also, it has very few parameters to tune over. Given both of those things, that's currently my go-to thing. And the general idea behind extra trees is, there was a slide I kind of went through pretty quickly, is the idea that it basically is made up of decision trees, where each decision tree sees a subsample of the data. So each tree on its own is a noisy learner, a very noisy learner. But you train up 2,000, 10,000 of these trees, and that aggregate learner is actually a much more robust learner. So it goes into the ideas of boosting and bagging and aggregate learners. And yes, it's slow to train because you're training up so many things, but I'm okay with time for now. Both, actually, extra trees supports regression and classification. And that's another reason. Uh, it has features which kind of make the best of a lot of different things. How features are selected at each node. Has the same issue. So that issue doesn't go away with many things. So you're asking about correlated features. Some of the things we do, it also helps with increasing the number of trees. So I'm talking 2,000, 3,000 trees, right? The likelihood of correlated features being selected by the same tree, very small, right? Across trees, you could get things and it'll diversify the features. There are some tricks we pull when we run extra trees or random forests, where what we will do is we'll insert a vector that's uncorrelated with our output. So within the training set, stick a noise random vector, which is uncorrelated with the output, train the model, and ask what the feature importance of this noisy vector is. And throw out every feature that's below that feature importance level. And that allows a way of sub-selecting features that are better for feature selection down the road. The other thing we recommend people doing is once you've received a set of features at some feature importance level as part of a model, take those features and run a pure and simple correlation with all the other features, especially for brain data, and threshold it at a very high level of correlation. Because there exists, especially if you're doing smoothing or other things on the brain, there will be other features that were highly correlated with a given feature. So that gives you a better sense of the overall space of features in the brain, which are predictive, and then refit the model with all of those features that you've selected just to show what the performance difference is between the original things that were selected and this extended set of correlated features that were added to it. And if that performance difference is a lot, then something is off. But if that performance difference is small, then you're actually in a good space of features. So a lot of tweaks to things beyond the thing, but these kind of help with. Depends on the problem. I mean, our default setting is at 2,500 now. But we will test out some things with smaller numbers of trees to get an asymptotic, well, to get a sense of performance. So the feature selection bit I talked about actually helps with that tremendously. And in general, we get about a 10% boost in performance across things that we have tried this on. Right? I'm going to stop. Oh, okay. Ah, okay. That's a good question. So the question is whether it's the prediction error that I care about more than the training error and its relation to understanding biological space or something else. Uh, I would say prediction error is what you want to drive low, even in your understanding of things, because even if your training error goes down, that doesn't tell you that it's a good model. It just says you have a model that puts training error down. Whereas if your prediction error goes down, that tells you an objective measure of a better model. And now you can do the understanding in the space of that better model. But this is where, I mean, correlated features come up in brain imaging a lot, right? So understanding how it's, what's important, I think, in this space is to understand that these are highly nonlinear models, multivariate nonlinear models. So to pick on a cluster or a voxel and say this feature means something to me is weird, because it's the combination of all these things that's basically giving rise to uh, the prediction. So understanding that this is a multivariate space as opposed to thinking about it as this brain region and that brain region, I think is important in the context of machine learning and imaging. The combination of all these voxels that have information towards the problem I have at hand. How it biologically functions, I have no idea. Not for me. For me, it's basically saying here's a mathematical formulation that tells me there's information in these voxels. I leave it up to other people to interpret things out of it. All right, I'm going to turn things off.